So we're going to start by talking about errors a little bit. I'm not going to go into all the basics of errors and floating point and things like that, which you may have seen in an earlier class, and if you're not, it is covered in the introductory section of the textbook. So as far as error goes, we're going to talk about some of the key things. So I'm going to say read section 1.1 to 1.2 on your own. And that's brief and relatively straightforward, hopefully. But it's kind of tedious writing it. When I start writing it all on the board, I'm just going to bore everybody. So what's our goal? We're applied mathematicians, we're numerical analysts, computational scientists, whatever you want to call us. Abstractly, this is what we're almost always doing. We're given a problem, but we know we can't solve it exactly because the solution is too complicated. So we want to come up with an approximation to the solution, and we're given some target accuracy, right? If the solution has to be correct to within 10 to the minus 2 or 10 to the minus 8 or whatever. It might, your problem might be, I'm trying to build a bridge and I need to put up this beam and I need to know how much steel I need in this beam so that the bridge doesn't fall, and I'm going to have some tolerance that I'm willing to accept, but I'm not going to accept too much error in this, because if the solution you give me has too much error, the bridge might fall down and then you're out of a job. So what's our goal? Approximate the solution of some problem to within some target accuracy. Okay, so this is all we're doing basically all semester, is we're going to solve this problem. Okay, f is some kind of operator. It might be a nonlinear function, it might be a differential equation, it might be some complicated combination of these things, we don't know. X is the thing we want to solve for. Right, maybe it's the density of a fluid in a nozzle. Maybe it's how much steel I was supposed to put into a beam. Could be all kinds of things. And D is the data I'm given. Okay, so I'm going to throw this question out to you. I said we're going to approximate the solution, right? Not get it exactly. So I'm going to ask you this question. Where does the error come from? There's plenty of places, so can you think of a few?
Loss.
Sorry, what was that?
Loss of significant figures.
Loss of significant figures. Okay, good. You said something I didn't hear it. The instruments you're collecting your data with, yeah.
Also, rounding and chopping.
So rounding errors. Rounding errors are sort of related to loss of significant figures, although there's different sources where this can happen.
The bridge is
sampling techniques.
Sampling techniques, okay. Right, so we don't, and we talked about this here. We don't know everything about everywhere, right? We're even with the data that we collect. If you're talking about trying to predict the weather, and we're taking temperature readings or pressure readings, we're not taking them everywhere. We're sampling this data, right? So sampling. Noise, yep. Yep. Limitations of the model, absolutely. So we might be using a model that has mistakes in it, or very often simplifications in it. Any others? mathematician method yet.
This seems more and more like we're just gonna be wrong.
So you're worried that we're going to be wrong. This is why we do numerical analysis. So this is why, I didn't just say approximate the solution. I said approximate to within a target accuracy. And that's why we want techniques to say, okay, given that we have all this error in our data or in our approximation of f, can we get a handle on how bad is the error going to be in x? And the answer is hopefully that yes, we could come up with some bounds and say, well, we obviously don't know the exact error, because if we knew the exact error, we just add that onto our result and get the exact answer. But we might be able to say, well, the error is less than 10 to the minus 3. I'm confident of that. So yeah, you should be worried that we're going to be wrong. But that's why we're mathematicians. Any others? I'll throw one more out here, because this does crop up, sadly. And the worst bugs are not the ones where you run your code and everything blows up, because then you're like, obviously something went wrong. The worst bugs are the ones where they do something subtle and you come out and the answer looks kind of reasonable. That's probably right. Those are the frightening ones. So here's a story about error. So I'm Canadian, so this is a Canadian story about error, but Americans are also very capable of having disasters due to errors. So this was, I think it was 1988, somewhere around there. They built a new grocery store, Save On Foods, in the Vancouver area. And it was going to have parking on the garage, on the deck of it. So the engineers, they did the calculations, they built the building. It was time for the grand opening of this new building. So it was great. They opened up the parking deck, the first car started to drive on, and the roof collapsed under the weight of them. So I have a picture of that. I'll let you guys pass around the picture of it. I'll post it on Canvas if you want to look at it. So, of course, they started an investigation into this and said, what went wrong? And it turns out a lot of little things went wrong. A lot of little things from here that nobody took into account. So I think the concrete on the roof was poured very slightly thicker than they originally expected. One of the sidewalks was a little bit wider than they thought. Some of the material, they swapped out one kind of material for a different kind of material, and it didn't weigh exactly the same amount. Somebody doing the calculations made an arithmetic error somewhere along the way. And all of these things were very small, very tiny, and unfortunately, tiny errors can propagate. We're going to see some examples of that where we make very small errors along the way, and they blow up on you. And that's why we do numerical analysis. So that's why we say we know there's going, these ones are the hardest ones sometimes to get rid of, and that's why you want to test your code carefully, and that's why I want you to test your code when you're doing it. But we want to get a handle on all of these. When we do our sampling, how far spread out apart is the data that we have, and how much is that going to affect things? We don't have infinite precision we're going to round. How much is that going to affect things? Now we do computations, we lose significant figures. How much is that going to affect things? And we can, as mathematicians, we can get a handle on these things. We can try to get a handle on these things and say at the end of the day, okay, I'm confident in this calculation, or I'm not quite confident yet in this calculation, and we need to do something else. So let's talk a little bit more about error. We'll hit some of these sources of error. Say what are the things we have to worry about. What are some of the ways that we can try to quantify what's going on here. Okay, so we mentioned, I think modeling error came up on here. So as part of modeling, there's obviously lots of issues. You might be ignoring friction or something like that, and there's also the issue of just that we come up with a model at the end of the day. It better be a well-posed model. So we need a well-posed model. right? So you've come up with some model for whatever problem you're trying to solve. Abstractly, it looks like this. We want to solve for x. Do you guys know what well-posed means?
It means that if we make a small change in the solution, on the initial condition, the whole solution will just change a little bit.
Okay, so that's part of well-posedness. That we usually say, when people say it differently, the solution should depend continuously on the data. So that means exactly what you just said, that if we were to change the data a little bit, right, and effectively the real data is a little off from what we've got in here because we've got errors in our measurements, we haven't sampled everywhere. So the real data is a little off from what we're using here. We don't want that to cause things to completely blow up on us, right? We want the solution that we get with maybe our slightly wrong data to be very close to the solution we would have gotten if we had exactly the right data on there. So that's what I mean by depending continuously on the data. Little change in data means little change in the solution, right? Not the jump. Yeah.
Does that mean we're ruling out model and chaotic systems?
Does that mean we're ruling out model and chaotic systems? So yeah, chaotic systems is a different ballgame, right? And if you have a chaotic system, what do you expect? You don't expect a weather forecast for 2 months from now to be accurate, right? Because chaos becomes an issue, right? So this is something to be aware of. You know, how far in time can I expect my model to actually, or my calculations to actually be realistic? And that's an important thing, a question to ask. Do you know what else is meant by well-posed?
You're not leaving out too many. The assumptions that you make, the variables that you input are not like ignoring some critical. Well, you're not ignoring some critical values in your model.
You don't want to ignore some critical value in your model, yeah. Okay, so there's actually well-posedness mathematically has a really precise meaning. And there's actually 3 parts to it. So we got one. One that's important is, what if my model looks like this? So I'm trying to solve for f equals 0, and my f looks like this. Is that well-posed? No. Why not?
X is never 0.
F is never 0, exactly. So one thing that you want is, once you've given me the model and said solve it, I hope there's actually a solution, right? Because if there's no solution, I'm kind of wasting my time. So a solution exists.
Solution is unique.
And the solution is unique. That's the last one. So if we're trying to predict how much steel do I need to put in the seam to make sure that my bridge doesn't fall down, you don't want me to come back and give you 2 different, very different answers and say, well, it's either this one or it's this one, right? The model can't tell the difference, right? You've got a bad model then, right? You need a model that there's only one answer to this question. Of course, we can have root finding problems that have multiple roots that we have to find. But for a well-posed problem, there should be one solution and only one solution. If there's more going on there, then we need to be aware of that, taking into account that we're looking at all possible solutions. So these are the 3 things that I mean by well-posedness. And if we don't have a well-posed model, then we need to step back and say, wait a minute, something is going on here. So we want it to be well-posed. A well-posed problem can still be kind of inherently hard to solve numerically. So let me give an example, a simple example. So all these things can be true. But still somehow this problem is not an easy one to get an accurate solution of. Okay, hard is a relative term. So, talk to any high school math class, they may think is a hard problem numerically. That's not exactly what I mean, but in fact, in some cases, it can be what I mean. So what do I mean here? We're not solving the problem exactly, right? We're not working with exactly accurate data. We're not going to get an exactly accurate solution. So what are we effectively doing? Instead of solving for x, x would be the holy grail. It's the real true solution. We're almost never going to get the real true solution to infinite precision. We compute it with some error. So we'll call it x plus delta x. Yeah.
How much of this, though, can be, or should I say, how much of this is desirable because we don't want to have overfitting, right? We want our model to be robust enough not to.
Yeah, overfitting. So overfitting we're going to see when we come to interpolation. So I don't think I'm talking about overfitting here. So
I guess my point is, like, can we distinguish between how much of the error received is desirable versus non-desirable? Like, we wouldn't want our model to fit too perfectly to maybe
right.
overfit.
So when I say fitting too perfectly, I'm not saying, given this data, I fit the data perfectly. I'm saying I have the ability to make predictions accurately, right? So if you overfit the data, right, you may fit the data exactly, but you're not able to make predictions accurately at all, right? Your predictions are way off. So when I say I want good accuracy, I want to match this correctly. But that's a really important question, overfitting, and we're going to see that a little later. So what do I get? I get something like this. Now this is one number that I have, right? I don't know which part is x, and I don't know which part is delta x. I just know that I've got this one number, and it's probably got some error in it. So you might say, effectively, I'm solving this problem. So f of x plus delta x, and maybe d plus delta d equals 0. In other words, I'm not exactly solving this problem. I'm in some sense solving a nearby problem, right, that has different data. Which again, I may or may not know exactly what that different data is. And we've talked about that here, right? If the error in the data is small, hopefully the error in x is also small. Okay, and we're going to say delta x, we're going to call the absolute error. And delta x divided by x is the relative error. Okay, you've seen this before. So here's an example. Nice simple problem. Okay, it's a linear system, 2x2 matrix. Okay, so we'll call this matrix A. This acts as my model in some sense. And this is my D. This is my D on my right-hand side. Okay, now we've run our numerical method, and somehow or other it's come up with an answer for us, right? Come up with an approximation. So, and the approximation that we get is, again, x plus delta x, and we don't know which part is x and which part is delta x, equals minus 1, 0. Okay, and so we look at this approximation, we say, is this solving the right problem? Well, an easy way to check, right, is let's plug this value in here, do the matrix vector multiplication, and see if we get something close to this right-hand side. We hope we do. Yeah. In an ideal world, we'd get exactly our right-hand side, but we know there's some error coming up, so we probably won't. But let's plug it in. So we do x plus delta x, and what do we get? We get minus 1, and then we get 0.99. That looks pretty close, right? So this component is correct. This component is off by about 1%. Not bad. Okay, so I'm going to call this again d plus delta d, where if we know our exact d is minus 1, 1, that means delta d is 0 and minus 0.01. Okay, delta d is small. That's what we wanted. A small delta d, a small error in our data means, okay, we haven't solved the exact problem, but we've solved a pretty nearby problem, you know, nearby to within 1%, say. So delta d is small. Implies that we solved a nearby problem. Okay, now this is a nice small enough toy problem that we can go figure out how well we did here, right? I can go through and solve this exactly. And if I do, what's the true solution? The true solution is x equals 1, 1. Okay, and you can easily plug this in here and verify that indeed this gives me the correct right-hand side. But the other thing that you can notice right away, 1, 1 is not very close to minus 1, 0, right? If I'm looking for that solution and you give me this solution, I'm probably not very happy with you. So what went wrong? This is a well-posed problem, right? This is an invertible matrix. There's only one solution. Okay, it's a linear system, 2 linear equations. So what are we effectively doing? We're finding the intersection of 2 lines. So can you guess what went wrong here? Why did we get such bad results?
The matrix is close to singular.
The matrix is close to singular, right? So this is an invertible matrix. But if you look at these rows, they're almost the same, right? So it's not singular, but it's close. So when I say we're solving for the intersection of 2 lines, what are these 2 lines doing? These 2 lines are nearly parallel. They're not quite parallel, but they're nearly parallel. Right? So when I said, great, delta d is small, well, delta d is going to be basically this distance here, right? This distance is going to stay small for a long time because these lines are nearly parallel. So delta d was small, but delta x is not so small. Okay, so in this case, nearly solving the problem is not quite the same as getting near to the exact solution, even though it's a well-posed problem. So something to be cautious about. And right, this wasn't anything to do with the numerical method that I used for this. I don't know what numerical method came up with this, but you can see here this is kind of inherent to the problem. The real problem was these 2 lines are almost parallel, right? And that even if my delta d is very small, my delta x could be huge.
So for well-posed models, solutions should depend continuously on data.
Right, and this solution does depend continuously on the data, but you've got a very big constant showing up in your definition of continuity.
You can be continuous in terms of ways. It can be linear, exponential.
You can be linear continuous in different ways, yes.
Yeah, so let's say, how do you adjust the method? What are ways of adjusting the method? Well, can you adjust the method to change how your model?
So can you adjust the
relates
method
data?
to kind of change how your method relates to the data? So sometimes, yes. So one thing here that you'd want to be able to do with this problem is to say, okay, I don't know the solution ahead of time, but somehow I recognize that this matrix is close to singular ahead of time. And I recognize that a small delta d is not going to be good enough. I'm going to need actually quite a small delta d in order to be good enough and to be able to quantify that. So we can quantify that a bit here. This is called This comes up in the condition number of the matrix, which tells you, how hard is this matrix going to be actually to invert. So you might use your condition number, or you'd estimate the condition number in real life. In real life, you're estimating everything, right? Which again, you say, well, I don't know the exact condition number, but I get a bound on the condition number. The bound on the condition number tells me that if delta D is, say, this small, then I'm good enough. And it might be that delta D is this small and my error is way less than I need, or it might be that delta D is this small and I just hit the tolerance that I need. So those are the kind of bounds you get, where you don't, so the error is less than this, and it might be much less than this, or it might be just hitting the tolerance. But as long as I'm hitting my tolerance, I'm happy. So yes, we use the condition number. Let's measure this effect using the condition number. So let's start here, again, kind of abstractly, and say this is the supremum over all delta D's that are non-zero. We're going to take the ratio of the relative error in X to the relative error in D. So in our example that we just did, the relative error in D was very small, right? It was on the order of 1%. The relative error in X was very large, right? So the condition number was large over small. What we'd like is to have this condition number ideally close to 1, that the kind of error that we make in the data is going to be proportional to the kind of error that we get out in our solution. So that would be the goal, a low condition number, a condition number close to 1 where our data error is going to be kind of on par with our solution error. If we estimate this and say, oh, this is a big number, then we know we need to be really careful. So if k is large, so say k is much bigger than 1, right, again, in other words, the data error can be very small while the solution error can be very large, then we're going to say that the problem is ill-conditioned. And on the other hand, if k is close to 1, which is good, again, that means error in the data is kind of on par with the error in the solution, then the problem is well conditioned. Okay, so number 1, we said we'd really like to have a well-posed problem, right? Like, don't ask me to solve a problem that has no solution, or the solution is sort of meaningless. But secondly, ask me to solve a problem, hopefully, where I actually have a chance of getting the answer right. So number 2, we certainly want a well-conditioned problem. And this actually can be a big issue when you're solving differential equations. Whatever numerical method you use, it almost always turns into you have to solve a gigantic linear system of equations. And depending on the type of method you use, some of these end up giving you matrices like this, matrices that are very ill-conditioned. An ill-conditioned 2x2 matrix, okay, maybe no big deal. An ill-conditioned million by million matrix, this might get you into some trouble. So in our example, when we were trying to solve AX equals D, and we said we actually solved this nearby problem. I think we called this D, not delta. Okay, so this was our AX, and then this term is going to be our A delta X. Okay, so what do we have? We have that delta X is equal to A inverse of D plus delta D. Of delta D. And X is equal to A inverse of D. And if I want to try to get a handle on the condition number, I'll say delta X over X divided by delta D over D. Okay, I can put all of this in terms of my matrix A and my data, right? The X and the delta X are unknown ahead of time. My data and my matrix are things that I've been given. So this, I said, is A inverse of delta D divided by A inverse of D. Okay, so I have some terms that involve delta D's, and I have some terms that involve D's. So if I put them all I sort of collect them, I have A inverse of delta D over delta D. This A inverse D is going to come into the denominator. I have a D that's going to come into the numerator. And I'm going to try to write it in a way that's kind of symmetric to this. I'm going to write it as A times A inverse D. Right, so this is A inverse acting on something divided by something. A acting on something divided by something. So it's got this sort of symmetric feel to it. And do you know, if I look at these individual terms, do you know what this kind of term would give me? If I want to find the biggest value it could possibly have over all delta D's, which is what I want for my condition number. Do you know what that gives you?
It's going to be A times delta X for the delta D.
Right, so we can put back in terms of X. There's actually a definition here, which you may or may not have seen. This is actually how we define a matrix norm. So we start with vector norms, right? And your vector norms, you know how to compute. Your infinity norm is the biggest component, or your L1 norm, where you add up the absolute value of the components, or things like that. Then we use the vector norms to define a matrix norm, right? So this delta D is a vector. A inverse times delta D is also a vector. So now I can use my vector norms and say that defines a matrix norm. So the biggest value this would ever take over all delta D's is how we define the matrix norm of A inverse. The biggest value this would ever take over all the A inverse D's in this case is how we actually define the matrix norm of A.
So that whole thing is going to be less than or equal to the norm of the inverse of the matrix times the norm of the matrix.
Exactly. So this whole thing is always going to be less than or equal to the norm of A inverse times the norm of A. And this is just how we define matrix norms. So this is how we define the condition number of a matrix. Right? So if I had the identity matrix here, so the norm of the identity matrix might be 1, and then its inverse is the same, also 1, and you get a perfect condition number, which makes sense, right? If I'm trying to solve I times X equals D, there's nothing to do. You're gonna get the right solution, right? So that's a good sanity check, right? Does this make sense when I put in the simplest thing of the thing? If it comes back and tells me that the identity matrix is ill-conditioned, then you might need to work on your definition. So for a matrix, the condition number of A is the norm times the norm of A inverse. Okay, and if I come back to my little 2x2 matrix, okay, I can compute the norm of this, the infinity norm of this. Do you know what the infinity norm of a matrix is?
We're gonna take the absolute value of the sum of the rows.
Yeah, it's the row sum, exactly. So the biggest row sum. Okay, that maybe makes sense because you imagine multiplying by a vector here. Say I multiplied by the vector, 1 minus 1. Then that would give me the row sum right here. And then the next component would give me the row sum of this. So in this case, the biggest row sum is, this is a little less than 3, this is equal to 3. So the norm of A is 3. That's the row sum, the biggest row sum. And if I look at A inverse, I'm just going to write it down. Again, in real life, we never ever write down the inverse of a matrix, but this is 2x2, so we're willing to risk it. Okay, in this case, here the row sum is 199. Here the row sum is 399. Yeah.
Why did you choose to do the infinity norm?
Why did I choose to do the infinity norm? It was just a choice. I could have chosen anything else. I chose it because it's simple. But there's certainly other norms. And the norm that you want to use is going to be typically dependent on the problem you're looking at and also the methods you're looking at. Will mean that one norm is maybe a lot easier to use or kind of make more sense. And this is problem specific. And again, this is why we're mathematicians and we come in and say what actually makes sense to look at here. If you're solving a problem that has a shock, looking at the L infinity norm might not make sense because if your shock location is just a teeny bit off, you have a huge jump in your solution, but your solution might actually line up pretty well. So there, an L1 type norm would typically be used if you have discontinuities. The kinds of problems I solve, which involve second order equations, usually I'm using L infinity norms because they're the easiest to analyze. Yeah.
So could something appear to be like ill-conditioned under one norm, but well-conditioned under
Can something be ill-conditioned under one norm and well-conditioned under a number?
appear to be?
Or appear to be. So for these finite dimensional problems, these norms they're called equivalent norms, which means basically you can bound one norm by a constant times another. So if you have a problem that's well posed and well conditioned in one norm, it should still be in another norm. The constant could be big though, certainly. And like I said, for problems with discontinuities, you're going to have real issues if you try to use an L infinity norm, whereas an L1 norm is going to make a lot of sense there. But for these finite dimensional problems, the normal and usual norms that we use are going to be equivalent. Okay, so what's my actual condition number? 1197, yeah. So what does that mean? Basically, I take my error in my data, which was 0.01, and I multiply it by 1200 almost to get the error in my solution, right? And that's why my 1% error resulted in a much larger actual error, right? And we could have predicted that might happen if ahead of time we'd computed the condition number or tried to estimate the condition number and said, now, if I know ahead of time this is going to happen, if I can say, well, my error in my solution might be on the order of, 1200 times delta D, then I can say, now I can estimate how small delta D needs to be in order for this to be reasonable.
That's what I was asking.
That's what you were asking before. But you still don't want to have to solve ill-conditioned problems if you don't have to. Because again, you could do this on a 2x2 matrix, but if you have a million by million matrix, which is a very realistic type of thing to be solving, you may have a hard time.
So when that happens, that we have an ill conditioning problem, so that we have to go back into the basic and analyze the whole model thing and figure it out. If we have a problem that we have to solve,
If you have a problem you have to solve and things are ill-conditioned, what do? That you spend months and months feeling confused sometimes. That's a realistic answer in research. But you might ask what's happening, why is it becoming ill-conditioned? And sometimes it can be the method that you're using is producing something ill-conditioned and you might need a different method. So this can happen with solving differential equations, that one method will lead to a very ill-conditioned matrix, but another method might not. So you might change the method you're using. The problem itself is inherently ill-conditioned and you really, really need to solve this problem. Then you're going to maybe throw money at the problem and say, I need to buy some time on a supercomputer. And that might be the solution, right? But I guess your first question is, where is this ill conditioning coming from, right? If I'm going to fix the problem, I need to know where the problem lies. Yeah.
So like how ill-conditioned something is kind of dependent on like your resources and what you're willing to compute. Like if you have
Sure.
10 years to compute something that has a really big condition over it.
Yeah, sure. So how ill-conditioned you're willing to deal with certainly depends on your resources. And okay, in real life, I'm probably not very bothered by a condition number of 1200 at all, right? Because I'm going to try to solve things to more than, say, 3 or 4 significant figures in real life, hopefully, right? So this may not be a big deal at all. It's a nice illustration for this toy problem. But certainly, if I say, well, I'm going to compute things to 6 significant figures, and then my answer will maybe have only 2 significant figures at the end of the day, that might be fine. If you have access to a good supercomputer and you happen to have lots of money in your grant to buy time on it, then you might not be too worried, or if there's no rush in the solution. Yeah.